Hello there, and welcome to The Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into the beginning of everything, into the question that has followed humanity for as long as we have been able to look up at the stars and wonder, how did the universe begin? But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a gentle reminder that, even as we talk about the vastness of the cosmos, we're all listening from our own small, quiet corners of it. Now, feel free to dim the lights. Maybe let a soft hum fill the room and allow yourself to settle into a comfortable position. And let's begin our journey together. And if your mind begins to drift, that's perfectly fine. You can simply follow along as long as you wish, or let the story carry you gently into sleep. The story of the universe begins about 13.8 billion years ago. It's a number we've come to accept, repeated in textbooks, documentaries, and quiet conversations about the nature of reality. But numbers, no matter how large, often fail to capture the true depth of what they represent. 13.8 billion years ago is not just a moment in time, it is the moment when time itself began. And that idea is where things start to become a little strange. Because when we ask how the universe began, we often find ourselves asking another question almost immediately. What came before it? It feels natural, almost unavoidable. Every story we know has something that came before. Every effect has a cause. Every beginning has something that led up to it. But here, that instinct may quietly fail us. Because if time itself began with the universe, then there was no before in the way we usually understand it. There was no earlier moment waiting in the wings, no ticking clock counting down toward creation. In a sense, asking what happened before the universe is a little like asking what lies north of the North Pole. It's not that the answer is hidden, it's that the question itself may not fully apply. And so, we find ourselves standing at the edge of something deeply unfamiliar. A beginning without a before, a moment that is not just the start of events, but the start of the very stage on which events can happen at all. Space, time, energy, matter, all emerging together, not inside anything, not expanding into some empty void, but rather expanding as space itself. It can be helpful, perhaps, to imagine this not as an explosion, but as a quiet unfolding, like a tightly folded piece of fabric, suddenly released, not into a surrounding room, but becoming the room itself as it stretches outward. There is no center you could point to, no edge you could approach, only distance growing, everywhere, all at once. At that earliest moment, the universe was unimaginably hot, dense beyond comprehension, filled with energy so intense that the structures we now take for granted, atoms, particles, even the idea of stable matter, could not yet exist. It was not a place, not in any familiar sense. It was a condition, a state of pure possibility. And yet, even as we describe it, there is something important to acknowledge. We do not fully understand how it began. Science has given us a remarkable ability to look back, to reconstruct the early stages of the universe with incredible precision. We can trace the cooling of that initial state, the formation of the first particles, the emergence of light, the gathering of matter into stars and galaxies. But the exact mechanism, the true origin of that first moment, remains just beyond our reach. And so, there is a quiet humility in this story. We know a great deal, but not everything. Some scientists have suggested that perhaps there truly was nothing before, that the universe is complete in itself, with no need for an external cause. Others imagine that what we call the beginning may be part of a larger cycle, or one of many universes, or the result of deeper structures we have yet to uncover. For now, these ideas remain possibilities, gentle outlines at the edges of understanding. But what we can say with confidence is that from that early searing state, the universe began to change. It began to expand, and as it expanded, it cooled. Very slowly, over vast stretches of time, the chaos of that first moment began to soften, to organize, to settle into patterns. Tiny fluctuations, barely noticeable differences in energy, began to matter. They would grow over millions and billions of years into something extraordinary, but at the beginning, they were almost nothing, a whisper of imbalance, a slight unevenness, the kind of imperfection that in most systems would simply fade away. And yet, here, those tiny irregularities would become everything. They would become the seeds of galaxies, the structure of the cosmos, the difference between emptiness and form, and eventually, the difference between a lifeless universe and one that could give rise to stars, planets, oceans, and minds capable of wondering about their own origin. It's a quiet thought, really, that everything you are, every atom in your body, every memory, every sensation, traces back in some way to those first subtle variations, not to something grand or deliberate, but to something almost invisible, as if the universe, in its earliest moment, leaned ever so slightly in one direction, and never quite returned to perfect balance. And from that gentle asymmetry, all of existence followed. For now, though, we remain at the threshold, at the moment where time begins, where space stretches into being, where the familiar rules have not yet fully formed, a place where our understanding becomes softer, more uncertain, but also, in its own way, more beautiful. Because sometimes the most meaningful part of a story is not the answer, but the quiet space where the question first appears. And as we continue, we'll begin to move forward, slowly, into that early universe, into the smallest moments imaginable, where reality itself flickers, shifts, and begins to take shape. As we linger at that quiet threshold, where time itself begins, it becomes clear that the story of the universe is not a single, neatly defined narrative. Instead, it feels more like standing in a dimly lit library, where several different books lie open at once, each offering a different version of how everything might have begun. And for now, we're not entirely certain which one, if any, is the true account. This may sound unsettling at first, but there is also something deeply calming about it, because it reminds us that the universe is still in many ways an unfolding mystery, and that our understanding is not a fixed destination, but a gentle process of discovery. One idea suggests that the universe may not have had a beginning in the traditional sense at all. In this view, time behaves differently at extreme scales. As we trace the universe backward, space and time begin to curve and soften, like the surface of a sphere. Eventually, the concept of a sharp starting point fades away. Instead of a sudden beginning, there is simply a smooth boundary, a place where asking what came before becomes as meaningless as asking what lies beyond the edge of a circle. It is not that something is hidden there, but that the idea of before no longer applies. Another possibility is more expansive, almost poetic in its scale. Imagine that what we call our universe is just one small bubble, floating within a much larger cosmic sea. In this picture, space is constantly stretching and generating new regions, each one becoming its own universe, with its own laws, its own constants, its own unfolding story. This idea is sometimes described as a multiverse, not a single universe, but many, perhaps infinitely many. Some of these universes might resemble ours, with stars, galaxies, and the quiet glow of distant light. Others might be very different, expanding too quickly for structure to form, or collapsing too soon, or governed by laws that would feel unfamiliar, even impossible to us. In this vast landscape of possibilities, our universe would be just one gentle outcome among countless variations, and the reason it appears so finely balanced, so capable of producing complexity and life, might simply be because only certain kinds of universes allow observers to exist within them. There is also a more cyclical vision of reality. Instead of a single beginning followed by endless expansion, the universe could be part of a repeating rhythm, expanding, slowing, and eventually contracting, only to begin again. In this idea, sometimes called a bouncing universe, the cosmos does not emerge from nothing, but from the remnants of a previous state, a prior universe perhaps that grew, aged, and then gently folded back into itself, setting the stage for a new beginning. Not a singular event, but a cycle, like breathing in and out, over timescales so vast they almost lose their meaning. And then there are ideas that stretch even further beyond our everyday intuition. Some theories suggest that the universe we experience, 3 dimensions of space and 1 of time, may be only a small part of a much larger structure. In these models, reality could contain additional dimensions, hidden from our perception, folded tightly into scales far too small for us to notice. Our universe, in this view, might exist like a surface, suspended within a higher dimensional space, and its beginning, its expansion, might have been triggered by events beyond our familiar dimensions, perhaps even by the interaction of larger structures we cannot directly perceive. It is a strange thought, that what we experience as everything could be just a thin layer of something deeper. And yet, even as these ideas become more abstract, they share something important. They all arise from the same place, from our attempt to understand, to extend the laws we know, to gently push them toward the edge of what is observable. Because despite all the possibilities, there is one guiding principle that remains constant. We are trying to describe the universe in a way that is consistent, that follows patterns, that makes sense of the evidence we can observe. And that evidence tells us something very clear. No matter which deeper explanation might eventually prove correct, our universe did begin in a hot, dense state. It did expand, it did cool, and from that early simplicity, it began to evolve. So while we may not yet know the ultimate cause, the deeper why behind existence itself, we do know what happened next, and that, in itself, is a remarkable achievement. Because by carefully observing the universe today, by studying the faint afterglow of its earliest light, by measuring the motion of galaxies and the subtle patterns hidden in the sky, we have been able to reconstruct a story that stretches back nearly to the very beginning. Not all the way, but close. Close enough that we can begin to describe the first moments, the earliest transformations, the birth of structure from near-perfect simplicity. And as we move forward into that story, something interesting begins to happen. The universe, which at first seemed beyond comprehension, begins to take on a kind of rhythm. It expands, it cools, it changes. And with each change, new possibilities emerge. For now, though, we remain just before those changes take hold, in a place where the rules are not yet fully formed, where the familiar distinctions between forces and particles have not yet separated, where reality itself feels fluid, uncertain, almost dreamlike. a place where even the smallest moment is almost too small to imagine. And as we gently continue, we'll begin to step into that moment, into the earliest fraction of time, so brief, so intense that all of existence was once contained within it. A moment where the universe was not yet filled with stars or galaxies, but with something far stranger, a flickering, restless foundation from which everything else would eventually emerge. As we move gently forward, past the question of how the universe might have begun, we arrive at something even more delicate, the very first measurable moment, a moment so small that even the word moment begins to feel too large. If you imagine a single second and then divide it, not into halves or quarters, but into smaller and smaller pieces far beyond anything we can experience, you would still not reach this scale. This earliest instant is often described as the smallest meaningful unit of time, a boundary beyond which our current understanding can no longer follow. It is not just very short, it is fundamentally indivisible, a kind of natural limit woven into the fabric of reality itself. In that fleeting instant, the entire observable universe, the vast expanse that now stretches across unimaginable distances, was compressed into a space so small that it defies visualization. Not merely smaller than a grain of sand or an atom, but smaller than anything we've ever been able to directly measure, a scale so tiny that even the concept of distance begins to blur. And within that tiny compressed state, the temperature was beyond anything we can meaningfully describe, not just hotter than the centre of a star, not just hotter than the most energetic events we observe in the cosmos today, but so intensely energetic that the very idea of matter, as we understand it, had not yet settled into form. At such extremes, the distinction between energy and matter becomes almost meaningless. They are no longer separate things, but different expressions of the same underlying reality. It is a place where everything is in motion, vibrating, shifting, exchanging form in a continuous and restless dance. And yet, even as we describe this early universe, something important must be acknowledged. This is where our theories begin to struggle, because modern physics rests on two incredibly successful frameworks. One describes the very large, the graceful motion of planets, stars, and galaxies, the gentle curvature of space itself under the influence of gravity. The other describes the very small, the strange and unpredictable behavior of particles, where certainty dissolves into probability, and outcomes can only be described in terms of likelihood. Each of these frameworks works beautifully within its own domain, but here, in this earliest moment, they are forced together, the vast and the tiny, the smooth and the uncertain, meeting in a single compressed state. And when they meet, they do not quite agree. The equations that describe the large begin to break down when applied to the small, and the rules that govern the small do not easily scale up to describe the entire universe. It is as though we have two maps, each detailed and accurate in its own region, but when we try to overlap them, the edges no longer align, and so this earliest moment remains partially hidden. Not because we have not tried to understand it, but because it lies just beyond the reach of the tools we currently have. There are ideas, of course, possibilities that attempt to bridge this gap. Some suggest that gravity itself might have a deeper, more fundamental description, one that behaves differently at extremely small scales. Others imagine that space itself is not smooth and continuous, but made up of tiny, discrete units, like pixels in an image, too small to notice at ordinary scales but crucial at the beginning. And there are even more abstract ideas. where the fundamental building blocks of reality are not points, but tiny vibrating strands whose patterns give rise to everything we observe. But for now, these remain explorations, carefully constructed, mathematically elegant, but not yet fully confirmed. And so, as we rest at this earliest boundary, it may help to let go of the need for precise detail. Instead, we can imagine the universe at this moment as something more intuitive, a state of overwhelming energy, a place where everything that could exist exists in potential, where distinctions have not yet formed, where the rules are still settling into place, if we were somehow able to witness it, not as observers with instruments, but as something more abstract, a presence within that early state. We would not see particles or structures. We would experience something closer to pure activity, a restless, shifting field of possibility, a kind of cosmic turbulence, not in space, but in the very structure of reality itself. And then, almost imperceptibly, something begins to change. The universe expands, just slightly at first, and with that expansion comes cooling. It's a simple relationship, one we are familiar with in everyday life. When something expands, its energy spreads out, and its intensity softens. A hot cup of tea left untouched slowly cools as its heat disperses into the surrounding air. In a similar way, though on a scale far beyond anything we experience, the early universe begins to lose some of its intensity, and as it cools, the conditions begin to shift, not abruptly but gradually, subtly, like the first hint of dawn before the sun appears. The chaotic high-energy state begins to give way to something slightly more structured, still strange, still unfamiliar, but now beginning to follow patterns we can start to describe. And with each tiny step forward in time, new possibilities open, new behaviours emerge. The universe does not yet resemble anything we would recognise, but it is no longer completely beyond comprehension. It is beginning to take shape, and in that gentle transition from the unimaginable to the barely describable, we find the first hints of order, the first signs that the universe, even in its earliest moments, is not random chaos, but something that can evolve, that can organise, that can give rise eventually to structure, to stars, and to us. For now, though, we remain close to that beginning, in a time where everything is still fluid, still unresolved, where the forces that shape reality have not yet fully separated, where the universe is still, in a sense, deciding what it will become. And as we continue, we will move deeper into that strange and fascinating state, where space itself may not be smooth, where reality flickers and foams, and where the foundations of everything we know begin to quietly emerge. As the universe continues its gentle expansion, just beyond that first, almost ungraspable instant, we enter a phase that is perhaps one of the most difficult to picture, and yet one of the most fascinating. Because here, space itself may not be smooth, not the calm, continuous stage we imagine when we look up at the night sky, but something far more restless, far more alive. If you run your hand across a polished table, it feels flat, steady, predictable. But if you were to shrink down, smaller and smaller, beyond the scale of dust, beyond the scale of atoms, you would begin to notice that the surface is not truly smooth at all. It becomes uneven, jagged, textured. Now imagine applying that idea not just to surfaces, but to space itself. At these earliest moments, space may behave less like a smooth fabric and more like a bubbling liquid, a kind of cosmic foam. Not foam as we see in waves on the ocean, but something deeper, more abstract, a ceaseless flickering of tiny distortions, appearing and disappearing so quickly that they never settle. This idea is often described as quantum foam, but rather than thinking of it as a technical term, it may help to imagine it as a constantly shifting landscape, a place where nothing stays still long enough to be clearly defined, where the very notions of here and there begin to lose their meaning. In our everyday experience, we expect things to have clear positions. A cup rests on a table, a chair sits in a room. But at these incredibly small scales, reality does not behave this way. Instead, everything becomes uncertain, not because we lack precision, but because uncertainty is built into the structure of nature itself. There is a limit to how precisely we can define things like position and motion at the same time. The more closely we try to pin something down, the more its other properties begin to blur. And in this early universe, uncertainty is not a small effect, it is everything. Space and time themselves fluctuate. Distances stretch and contract, not gradually but spontaneously. Moments flicker, appearing and dissolving almost as soon as they form. It is a kind of instability that is difficult to imagine, because it is so far removed from the stable world we're used to. And within this restless foam, something even stranger may occur. Tiny regions of space may briefly collapse under their own energy, forming what we might call miniature black holes. Not the massive, star-consuming objects we think of today, but fleeting microscopic distortions, forming and vanishing in an instant. At the same time, space could twist in such a way that distant regions momentarily connect, forming short-lived tunnels, like tiny bridges that appear and disappear before anything can pass through them. These phenomena are not observed directly, but arise naturally from the rules that govern the very small, and while they may sound exotic, in this early epoch, they would not be rare. They would be everywhere, part of the constant dynamic texture of reality itself. It is important to remember that this is not chaos in the sense of disorder without meaning. It is structured unpredictability, a system governed by rules, but rules that allow for constant fluctuation, like the surface of boiling water, where bubbles form, expand, and collapse, not randomly, but as part of an ongoing dynamic process. Except here, the water is space itself, and the bubbles are fluctuations in existence. If we could somehow observe this state, not with eyes, but with a deeper kind of awareness, we would not see objects or shapes. We would experience something more like a restless field, a shimmering instability, where potential constantly rises and falls, a universe not yet settled, not yet defined, but already alive with activity. And yet, even in this turbulent state, there is a direction, because the universe continues to expand, and as it expands, it cools. This cooling is subtle at first, but its effects begin to accumulate. The fluctuations remain, but they begin to soften. The extreme energy that drives the most violent distortion starts to diminish, and slowly, almost imperceptibly, the foam begins to calm, not completely, not all at once, but enough that patterns can begin to persist, just a little longer than before. It is like watching a storm gradually lose its intensity. The waves are still there, the wind still moves, but the sharpest edges begin to smooth out, and in that softening, something new becomes possible. Stability. The kind of stability that allows structures to form, not permanently at first, but long enough to matter. This transition is quiet. There is no sudden moment where the universe announces that it has changed. Instead, it is a gradual shift, a gentle leaning toward order. And as this happens, another transformation begins to take shape. The forces that govern reality, which at higher energies seemed unified, indistinguishable. begin to reveal their differences. At the highest energies, it was difficult to tell one interaction from another, like a rapidly spinning coin, where you cannot distinguish heads from tails, only the blur of motion. But as the energy decreases, as the spinning slows, the two sides begin to separate, distinct, recognizable. In the same way, the fundamental interactions of the universe begin to emerge as separate influences, not all at once, but step by step. Each transition bringing the universe closer to the structured reality we know. And so, from this foaming, flickering beginning, something remarkable begins to unfold, not a sudden creation of order, but a gradual emergence, a quiet settling, a shift from pure possibility toward defined existence. And as we continue, we will begin to see how these emerging differences, these separating forces, start to shape the universe in deeper ways, how they guide the behavior of matter, the flow of energy, the formation of everything that will come. But for now, we remain in this in-between state, where reality is still fluid, still uncertain, but no longer completely unformed, a universe that is beginning, slowly, to take on the first hints of structure. As the early universe continues to expand, and the restless texture of space begins to soften, another quiet transformation unfolds. Not something you could see, not something that would announce itself with a sudden change, but something more subtle. The forces that shape reality begin to separate. Today, we are familiar, at least in name, with four fundamental ways that things in the universe interact. There is gravity, the gentle pull that keeps your feet on the ground, that holds the moon in orbit, that guides galaxies through space. There is electromagnetism, responsible for light, for electricity, for the attraction between charged particles, and for nearly everything we experience in our daily lives. And then there are two forces that are less visible but just as essential. The strong interaction, which binds together the tiny building blocks inside atomic nuclei, holding them tightly despite their natural tendency to push apart. And the weak interaction, which allows certain kinds of transformations to occur, enabling particles to change their identity, a process that plays a crucial role in the life of stars. These four forces may seem entirely different from one another. They operate on different scales, with different strengths, producing very different effects. But as we move back into the earliest moments of the universe, that distinction begins to fade. At extremely high energies, when the universe was far hotter and denser than anything we can recreate today, these forces may not have been separate at all. Instead, they may have been unified, a single underlying interaction, expressing itself in a way that only later becomes differentiated. It can be helpful to imagine this with a simple image. Think of a coin spinning rapidly on a table. While it spins, you cannot clearly see heads or tails. There is only a blur, a continuous, indistinct motion. But as the coin slows, the blur resolves. Two distinct sides appear, heads and tails. In a similar way, the forces of nature may have begun as a unified blur, indistinguishable at high energy. And only later, as the universe cooled, did they separate into the distinct interactions we observe today. This process is not abrupt. It does not happen all at once. Instead, it unfolds gradually, in stages. At first, one of the forces begins to behave differently, subtly breaking away from the others. Then, as the temperature continues to fall, further separations occur, each step revealing more structure, more distinction, more complexity. This idea that forces can unify and then separate is not just speculation. It arises from the patterns we observe when we study how these interactions behave at different energies. In experiments, when particles are accelerated to higher energies, the strengths of certain forces begin to converge. They start to resemble each other more closely, hinting at a deeper connection. Although we cannot yet reach the extreme conditions of the early universe, these clues suggest that unity may indeed lie beneath the diversity we see today. And as this separation unfolds, something important happens. The rules of the universe become more defined. At the highest energies, when everything was unified, behavior was governed by a single, overarching interaction. But as distinctions emerge, so do new possibilities. Different forces allow for different kinds of structure. Gravity shapes the large-scale curvature of space, guiding the motion of matter across vast distances. Electromagnetism governs the behavior of charged particles, enabling the formation of atoms, the emission of light, the chemistry that underlies life. The strong interaction holds atomic nuclei together, making stable matter possible, and the weak interaction allows particles to transform, enabling processes that release energy in stars and shape the evolution of elements. Each force adds a layer of complexity, a new dimension to how the universe behaves, and all of them trace their origin back to this early period, when they were still part of a unified whole. There is something quietly profound in this idea, that the diversity we observe today, the rich tapestry of interactions that make up reality, may have emerged from a deeper simplicity, not by adding complexity, but by revealing it, as if the universe began as a single note and gradually unfolded into a full, intricate melody. And this unfolding is closely tied to temperature, to energy, to the gentle cooling that accompanies expansion. As the universe grows larger, its energy spreads out, intensity decreases, and with that decrease, the unified state becomes unstable. It chooses, in a sense, to separate, not by intention, but as a natural consequence of the changing conditions. Much like how water, when cooled, begins to freeze, forming distinct patterns out of what was once fluid and uniform. The early universe undergoes similar transitions, not freezing into solid matter just yet, but shifting into new phases, where different behaviors become possible, and with each transition, the foundation of the universe becomes more structured, more capable of supporting the complex phenomena that will follow. For now, we are still far from stars, far from atoms, far from anything that resembles the world we know. But something essential has taken place. The forces that will govern everything, from the smallest particles to the largest galaxies, have begun to take on their individual identities. The stage is being set, quietly, gradually, almost imperceptibly. And as we continue, we will begin to see how this evolving framework, this emerging set of rules, guides the next transformation. A sudden and extraordinary expansion, so rapid, so vast, that it will reshape the entire universe in an instant, an expansion that takes the small and makes it immense, and carries with it the faint imprints of those early fluctuations, stretching them across the cosmos. For now, though, we remain in this delicate moment, where unity is giving way to diversity, where the universe is learning, in its own quiet way, how to become more than it was at the start. As the forces of nature begin to settle into their distinct roles, as the early universe continues its quiet cooling, something extraordinary is about to happen. A transformation so sudden, so vast, that it reshapes everything that follows. Up to this point, the universe has been expanding, but in a steady, gradual way. Now, for a brief moment, that changes. The expansion accelerates, not just a little, but dramatically. space itself begins to stretch at a rate that is almost impossible to imagine. Distances double, and then double again, and again, faster than anything we encounter in everyday experience. This phase is often described as inflation, but rather than thinking of it as a technical term, it may help to picture something more familiar. Imagine holding a sheet of paper, now fold it in half, and again, and again. With each fold, the thickness grows. At first it seems manageable, but after just a few folds, the stack becomes surprisingly thick. If you could continue folding far beyond what is physically possible, the thickness would grow enormously. In the early universe, something similar happens, not through folding, but through expansion. Space stretches so rapidly that a region once smaller than anything we can visualize becomes vast in an instant. Not over minutes or hours, but in a tiny fraction of a second. So brief that it slips past our intuition. This sudden growth has profound consequences. Before this expansion, different regions of the universe were close enough to influence one another. They shared the same conditions, the same temperature, the same underlying properties. But as inflation unfolds, those regions are carried far apart, so far that they can no longer interact. And yet, because they began in contact, they retain a remarkable similarity. This helps explain something that might otherwise seem puzzling. When we observe the universe today, even in regions separated by enormous distances, we find that it looks strikingly uniform. The temperature of the cosmic background light, the distribution of matter, the overall structure, all appear incredibly consistent across vast scales. Inflation provides a gentle explanation. It suggests that these regions were once close, once connected, before being stretched apart, like patterns drawn on the surface of a balloon, expanding as the balloon inflates, maintaining their relationships even as they move farther away. Another consequence of this rapid expansion is that it smooths out irregularities. Imagine a crumpled piece of fabric. As you stretch it, the wrinkles begin to flatten. The surface becomes more uniform. In a similar way, inflation smooths the geometry of the universe. It reduces curvature, making space appear on large scales almost perfectly flat. Not flat in the sense of being two-dimensional, but flat in the sense that parallel lines remain parallel, that the rules of geometry behave in a consistent, predictable way across vast distances. And yet, this smoothing is not complete, because even in this rapid expansion, tiny fluctuations remain. Small variations in energy, subtle differences from one region to another. At the beginning, these differences are incredibly small, almost imperceptible. But inflation stretches them, amplifies them, carries them outward across the expanding universe. What were once microscopic variations become macroscopic patterns, faint imprints, embedded in the structure of space itself. These tiny irregularities will later grow, slowly, patiently, under the influence of gravity. They will draw matter toward them, forming denser regions, eventually giving rise to galaxies, stars, and everything we see in the cosmos today. It is a quiet but profound idea that the larger structures in the universe, vast clusters of galaxies, enormous filaments stretching across space, all trace their origin back to tiny fluctuations in the earliest moments, small differences gently stretched, becoming the seeds of everything. There is also something else to consider. Inflation may not have happened everywhere in exactly the same way. In some models, while one region of space finishes this rapid expansion, other regions continue, stretching further, creating new pockets, new domains. This leads to the possibility that our observable universe, the part we can see and measure, is just a small portion of a much larger whole, a single region where inflation has slowed, allowing structure to form. Beyond it, there may be other regions, still expanding, still evolving, perhaps with slightly different properties. We cannot directly observe these regions. They lie beyond our cosmic horizon, beyond the limits of what light has had time to reach us. But there, possibility adds another layer of depth to our understanding, a reminder that what we see may not be all that exists, and yet, even within our observable universe, the effects of inflation are written into the fabric of reality. They are encoded in the faint patterns of ancient light, in the distribution of galaxies, in the overall shape and behavior of space itself, subtle clues left behind by a brief but transformative event. As this rapid expansion comes to an end, the universe transitions once again. The pace slows, the dramatic stretching gives way to a more measured growth, energy redistributes, conditions stabilize, and the universe, now vastly larger than before, continues its journey, cooling, expanding, evolving. What was once compressed into an almost unimaginable state has been carried outward, stretched across immense distances. But within that expansion, something has been preserved. Those tiny fluctuations, those faint irregularities, now spread across the cosmos, quietly waiting. They are not yet galaxies, not yet stars, but they hold within them the blueprint of what will come. And as we continue, we will begin to see how those small differences, those gentle variations in energy, begin to shape the universe in deeper ways, how they guide the flow of matter, the formation of structure, the emergence of complexity. For now, we can pause and take in the scale of what has just occurred. A universe that began in an almost inconceivably small state, suddenly expanding, becoming vast, smooth, and filled with the faint seeds of everything that will follow. As the great expansion begins to slow, as the universe settles from that brief, extraordinary growth, something quiet remains, something small, so small that, at first, it might seem insignificant, but in time, it will become everything. These are the tiny fluctuations, the faint irregularities in energy that were present even before inflation began. In the earliest moments, the universe was not perfectly uniform. It was almost uniform, but not quite. There were slight differences from one place to another, tiny variations, like gentle ripples on an otherwise calm surface. During inflation, those ripples were stretched. What once existed on scales far smaller than anything we could imagine was carried outward, expanded across the growing universe, and as they stretched, they became imprinted into space itself, frozen in place, like faint patterns pressed into soft clay. If we could look at the universe shortly after this period, we would not see galaxies or stars. We would see something much more subtle, a nearly uniform sea with slight variations in density. Some regions just a little denser than others, some just a little less. Differences so small that they would be almost invisible, if not for their long-term consequences. Because gravity, though gentle, is persistent. Where there is slightly more matter and there is slightly more pull, and over time, that pull begins to gather more material, slowly, patiently, almost imperceptibly at first. Imagine placing a few extra grains of sand on a flat surface. At first, nothing seems to happen, but if more grains continue to arrive, drawn toward that slightly higher point, a small mound begins to form. Then, over time, that mound grows. The same process unfolds in the universe. but on scales so vast that they stretch across millions of light years. Regions that were just a little denser begin to attract more matter, and as they do, they grow even denser. A gentle feedback, building structure from subtle beginnings. Meanwhile, less dense regions, with weaker gravitational pull, gradually lose material, becoming emptier, more open, forming the vast cosmic voids we observe today. And so, from those initial fluctuations, a pattern begins to emerge, not random, but structured. A network of dense regions, connected by filaments, surrounding vast empty spaces. What we now call the cosmic web. It is one of the most striking features of the universe, a kind of large-scale architecture, spanning billions of light years, shaping the distribution of galaxies across space, and all of it traces back to those tiny variations stretched during inflation. There is something deeply calming in this idea, that complexity does not always require dramatic beginnings, that even the smallest differences, given enough time, can grow into something extraordinary. But there is another layer to this story, because these fluctuations were not entirely random. They followed patterns, subtle statistical properties governed by the underlying physics of the early universe. When we observe the faint afterglow of that early time, the ancient light that still fills the cosmos, we can see these patterns, not directly as structures, but as variations in temperature. Tiny differences, so small that they require precise instruments to detect, and yet, those differences carry immense meaning. They are like a map, a snapshot of the universe when it was still young, still simple, still close to its origin, a record of the initial conditions from which everything else emerged. If you imagine taking a photograph of a calm lake, just as a gentle breeze begins to ripple its surface, you might capture faint patterns, small waves, slight distortions. Those patterns would not yet be large, but they would contain the seeds of motion. In the same way, the early universe holds within it a kind of blueprint, a quiet imprint of what will come, and over billions of years, that blueprint unfolds. Gravity amplifies the differences. Matter flows along invisible pathways, drawn toward denser regions. Gas clouds begin to form. They collapse, heat up, and eventually ignite. The first stars are born, but all of that lies ahead. For now, we remain in this earlier phase, a universe filled not with luminous objects, but with potential, a vast, dim landscape, shaped by slight variations, where structure is beginning to emerge, but has not yet fully taken form. It is a slow process, not something that happens in moments, but over immense stretches of time, and yet even in this slowness, there is direction. A quiet movement from simplicity toward complexity, from uniformity toward structure, from possibility toward form, and it all begins with something so small, so subtle, that it could easily be overlooked. A reminder that in the universe, as in many things, the most important changes often begin quietly, almost invisibly, before gradually and inevitably becoming everything. As we continue forward, we will begin to see how these growing structures interact with the cooling universe, how matter itself begins to take on more stable forms, and how the ingredients of everything we know begin to emerge from this evolving cosmic landscape. For now, we can rest in this moment, where the universe, still young, still quiet, carries within it the faint echoes of its earliest fluctuations, echoes that will one day become galaxies, stars, and the very fabric of our existence. As the universe continues to expand, and the faint patterns left by those early fluctuations begin to settle into place, something new begins to emerge. Not yet atoms, not yet light in the way we recognize it, but something more fundamental, the very first building blocks of matter. Up to this point, the universe has been a kind of restless sea, filled with energy, shifting, flowing, transforming from one form into another. There are no stable structures, no lasting identities, only motion and possibility. But as the temperature continues to fall, just slightly, the conditions begin to change. Energy, which once moved freely and without constraint, begins to take on more stable forms. It is as if the universe, which was once entirely fluid, begins to allow small pockets of structure to appear, brief at first, fragile but meaningful. These are the first particles. Not particles in the sense of tiny solid objects, but more like localized patterns, small stable ripples in a deeper field, each one representing a particular kind of behavior, a specific way that energy can organize itself. Some of these particles carry what we might think of as matter. Others carry energy or mediate interactions. But at this stage, those distinctions are still soft, still blending into one another. To make this more intuitive, imagine a calm lake. If you drop a pebble into the water, ripples spread outward. Now imagine that instead of fading away, some of those ripples become stable. They continue to exist, holding their shape, moving through the water without disappearing. In a sense, particles are like those stable ripples. They are not separate from the underlying lake, but expressions of it, patterns that persist. And in this early universe, many such patterns begin to form. Some are incredibly short-lived, appearing and vanishing almost instantly. Others begin to last longer, interacting with one another, combining, transforming. Among these early particles, there are a few important families. There are particles that will eventually make up matter as we know it. And there are particles that carry forces, allowing interactions to occur. But rather than naming them all at once, it may be more helpful to think in terms of roles. Some particles are like building blocks, others are like messengers. Some define structure, others allow change, and all of them emerge from the same underlying energy. There is a beautiful simplicity in this, that what we think of as stuff, the solid world around us, and begins not as solid at all, but as patterns in something deeper. As the universe continues to cool, these particles begin to interact in more stable ways. Certain combinations become favored, certain transformations become less likely, and gradually, a kind of order begins to form, not imposed from outside, but arising naturally from the changing conditions. At this stage, one of the most important ideas to understand is that matter and energy are not truly separate. They are deeply connected, different expressions of the same underlying reality. In everyday life, we tend to think of matter as something solid, something permanent, a table, a stone, a body, and energy as something more abstract, something that flows or moves. But in the early universe, as that distinction fades, energy can become matter, matter can become energy. Not metaphorically, but physically. Under the right conditions, one transforms into the other. In the high-energy environment of the early universe, this transformation happens constantly. Particles appear and disappear. They emerge from energy, interact, and sometimes convert back again. It is a dynamic equilibrium, a balance of creation and transformation. And as the universe cools further, this balance begins to shift. Energy becomes less concentrated. Transformations that once happened easily become less frequent. Particles that form are more likely to remain, to persist, to build upon one another. This marks an important transition from a universe where everything is constantly changing to one where some things begin to last, and with persistence comes the possibility of structure, of complexity, of the long chain of events that will eventually lead to atoms, molecules, stars, and life. There is also something quietly profound in the way these particles behave. They are not tiny billiard balls moving through empty space. They are better understood as excitations, as localized vibrations in underlying fields that fill the universe. Even in what we call empty space, these fields are present, they are always there, and particles are simply the moments when those fields become active, when they ripple in specific stable ways. It is a subtle shift in perspective. From thinking of the universe as made of objects, to thinking of it as made of activity, of patterns, of relationships. And yet, from this abstract foundation, everything familiar will eventually emerge. As the universe continues to expand and cool, these early particles begin to combine, to form slightly more complex structures, still not atoms, not yet, but moving in that direction, step by step, transition by transition, each one opening the door to new possibilities, and all of it unfolding quietly, naturally, without any guiding hand, just the gentle interplay of energy, cooling, and time. For now, we remain in this stage, a universe filled with particles, interacting, transforming, beginning to persist. A place where matter is not yet solid, but is no longer entirely fluid. A place where the first true building blocks of existence are beginning to take shape. And as we continue, we will begin to explore something that may seem simple at first, but carries deep significance. Why things have weight, why some particles move freely, while others seem to resist. A question that leads us, not to solid objects, but to an invisible presence, quietly filling all of space. As the first particles begin to settle into more stable forms, as the universe cools just enough for patterns to persist, a new question quietly emerges. Why do some things feel heavy, while others move freely? It may seem like a simple question. After all, in everyday life, weight feels obvious. A stone resists your hand when you try to lift it. A book presses gently against your palm. Your own body feels anchored to the ground beneath you. But in the early universe, before stars, before atoms, before anything familiar, this idea of weight is not yet fully formed. Because weight, or more precisely, what we call mass, is not simply something that objects possess. It is something that arises from interaction. To begin to understand this, it may help to imagine walking through a crowded room. At first, the room is empty. You can move freely, effortlessly, gliding from one side to the other without resistance. Now imagine the room slowly filling with people. As you try to walk, you begin to slow down, not because you're heavier in any literal sense, but because your movement is being influenced. Each step requires a little more effort. You are interacting with the crowd, and that interaction creates resistance. Now imagine that some individuals move through the crowd more easily than others. Some slip through with barely any disturbance. Others become surrounded, slowed, almost held in place by the interactions around them. In this analogy, the crowd represents something that fills all of space, something invisible, always present, even in what we might think of as empty regions. And the way different particles move through this crowd determines how much resistance they experience. This is a gentle way of thinking about what physicists describe as the Higgs field. Rather than imagining it as a complex mathematical structure, it can be helpful to think of it as a quiet background presence, permeating the entire universe, It is everywhere, not localized, not confined to a particular region, but woven into the fabric of space itself. And particles, as they move through this field, interact with it in different ways. Some particles pass through almost unaffected. They move freely, as if the room were still empty. Others interact more strongly. Their motion becomes slowed, not in speed alone, but in how they respond to forces. They resist change, and that resistance is what we perceive as mass. It is not that mass is a substance, something you can isolate or hold. It is more like a property of interaction, a measure of how strongly something engages with this underlying field. This idea can feel counterintuitive, because we are so used to thinking of objects as solid, as inherently heavy. But in this deeper view, what we call mass is not a fundamental ingredient, but an emergent quality, a result of relationships. There is also another layer to this, even beyond this interaction. Much of the mass we observe in the universe does not come from individual particles themselves. It comes from the energy associated with their interactions. For example, within the tiny cores of atoms, particles are bound together by powerful forces. They move, they interact, they exchange energy, and that energy contributes to the overall mass of the system. In a quiet way, this means that much of what we experience as weighty is not simply the presence of matter, but the energy contained within it. Energy held in place. Energy expressed in a stable form. It is a subtle shift in perspective, from seeing the world as made of solid objects to seeing it as patterns of energy, interacting, stabilizing, persisting. And yet, from this abstract foundation, everything familiar emerges. The ground beneath your feet, the weight of your body, the feeling of holding something in your hands, all of it arising from these invisible interactions, returning to the early universe. This process begins gradually. As conditions cool, as particles become more stable, their interactions with the underlying field begin to matter more. Some particles acquire this resistance, this tendency to persist, to respond more slowly to change. Others remain light, almost unaffected. And this difference becomes crucial, because mass influences how particles behave. Heavier particles move differently, they interact differently, they combine in different ways, and as these differences accumulate, they begin to shape the evolution of the universe. They determine which structures can form, which interactions dominate, which paths remain open, and which quietly fade away. It is as though the universe is developing texture, some parts dense, some light, some responsive, some more stable. A rich landscape, emerging from simple rules, and all of it guided by this quiet, invisible presence, filling space, influencing motion, shaping behavior. There is something almost poetic in this, that weight, something we feel so directly, so physically, is not a fundamental object, but a relationship, a conversation between particles and the fields that surround them, a gentle slowing, a subtle resistance, arising from connection. And as we continue forward, this emerging structure, this interplay between particles and mass, will lead to something even more profound, because not all particles will survive, not all will persist. In fact, for a brief moment, the universe will be filled with equal amounts of matter and its mirror image, and then, almost entirely, one will disappear, leaving behind just enough for everything that follows. As particles begin to settle into more stable forms, as the quiet presence of mass starts to shape how they move and interact, the universe reaches a moment that is both subtle and absolutely decisive. a moment that determines whether anything will exist at all. Because in this early phase, something remarkable is happening. Particles are not only forming, they're also meeting their opposites. For every particle of matter, there is a counterpart, a mirror version, almost identical, but with opposite properties. When these pairs meet, they do not simply bounce apart or combine into something larger. They disappear completely. Their mass, their structure, all of it is converted back into energy, released and carried away. It is a quiet kind of disappearance, but a total one. If you imagine writing something on a piece of paper and then gently erasing it until no trace remains, that is similar to what happens here. Matter and its mirror counterpart meet and leave behind nothing but energy. And in the earliest moments of the universe, this process happens constantly. Particles appear, their counterparts appear, and when they meet, they vanish. A continuous cycle of creation and cancellation. At first, this balance is nearly perfect. For every particle, there is a partner. For every bit of matter, an equal amount of its opposite. If this balance had remained exact, the outcome would be very different from the universe we know. Everything would have disappeared. All matter, all structure, all possibility of stars, planets, or life. Gone, leaving behind only a thin sea of energy, expanding, cooling, but never forming anything lasting. A universe without structure, without complexity, without observers, and yet that is not what happened. Instead, something slightly different occurred. A tiny imbalance, not large, not dramatic, just a small difference, almost imperceptible at first. For every vast number of particle pairs, there was a slight excess of matter, a few extra particles that did not have counterparts to cancel them out. And when the great wave of annihilation passed, when matter and its mirror counterpart met and vanished, those extra particles remained, quietly, almost unnoticed, but essential. It is from this small remainder that everything we see today is built. Every star, every galaxy, every atom in your body, all of it, tracing back to that slight imbalance. It is a humbling thought. That existence itself may depend on a difference so small it could easily have gone the other way. A universe that almost erased itself, but didn't. The natural question, of course, is why? Why was there more matter than its opposite? Why was the balance not exact? This is one of the deepest mysteries in modern physics. We know that certain processes in nature are not perfectly symmetrical, that under specific conditions, tiny preferences can emerge, small tendencies, favouring one outcome over another. In the early universe, these subtle asymmetries may have played a role. Perhaps certain interactions allowed matter to form slightly more often than its counterpart. Or perhaps the laws governing these particles are not perfectly balanced, containing a faint bias, hidden within their structure. There are also ideas involving elusive particles, ones that rarely interact, that pass through matter almost unnoticed. These particles may behave differently in ways that tip the balance, creating just enough asymmetry for matter to survive. But for now, these remain possibilities, carefully studied, deeply explored, but not yet fully resolved, and so we are left with a quiet truth. We do not know exactly why this imbalance exists, only that it does, and that it was enough. As the universe continues to expand and cool, the conditions that allowed particles and their counterparts to easily form begin to fade. Energy becomes less concentrated. Transformations that once happened constantly become rarer, and the surviving matter, those extra particles, begin to dominate. They no longer face immediate cancellation. They begin to persist, to interact, to combine, And with persistence comes the possibility of building. Small structures begin to form, not yet atoms, but the components that will eventually become them, a foundation quietly assembling itself. There is something deeply moving in this moment, not because it is dramatic, but because it is so easily overlooked. A tiny difference, a slight imbalance, and yet, without it, there would be no stars, no planets, no life, no questions, no quiet moments like this one. It is a reminder that the universe does not always require grand events to change its course. Sometimes, the smallest deviations, the faintest preferences, are enough to shape everything that follows. As we move forward, the universe continues its slow transformation, cooling further, allowing the surviving particles to come together in more stable ways, to form the first atomic nuclei, simple at first, but crucial. Because from these early building blocks, everything more complex will eventually emerge. For now, we remain in this delicate transition, where matter has survived, just barely. And the stage is set for the first true act of creation, not creation from nothing, but creation from what remains. A universe that nearly cancelled itself, now beginning, quietly, to build. As the quiet imbalance leaves behind a small but enduring trace of matter, as those surviving particles begin to move freely through an expanding, cooling universe, a new phase begins, not sudden, not dramatic, but steady and deeply important. Because now, for the first time, matter begins to combine. Up to this point, particles have existed mostly on their own, interacting, transforming, but rarely forming lasting structures. The universe has still been too hot, too energetic, for anything stable to take shape. If you imagine trying to build something delicate, like stacking small pieces of glass in the middle of a storm, it would be nearly impossible. Every attempt would be disrupted. Every structure would fall apart almost as soon as it formed. But now, the storm is beginning to calm. The temperature continues to fall. Energy spreads out, becoming less intense. And as it does, particles begin to linger near one another just a little longer. Long enough for something new to happen. They begin to bind, gently at first, tentatively, but with increasing stability. Among the most important of these particles are two types that will play a central role in everything that follows. One carries a slight positive character, the other is neutral. Together, they form the cause of what will eventually become atoms. But at this stage, they are still separate, moving through space, occasionally encountering one another. And when they do, under the right conditions, they can combine. This process is not immediate, nor is it guaranteed. Even as the universe cools, it is still filled with high-energy light, constantly moving, constantly interacting. Whenever these early combinations form, they are often broken apart again, like fragile structures that briefly assemble, only to be undone by the surrounding energy. And so, for a time, there is a kind of balance, formation and destruction, happening side by side. But as expansion continues and the temperature drops further, the balance begins to shift. The destructive influences weaken. The universe becomes just calm enough for some of these combinations to survive. The first stable pairing that emerges is simple but profound. A small nucleus made of two particles bound together. It is one of the earliest building blocks of matter as we know it. And once it forms, it opens the door to something more, because now additional particles can join, creating slightly larger nuclei, still simple, still limited in variety, but more complex than anything that existed before. Over a relatively short span of cosmic time, these processes give rise to a small family of elements, the simplest and most abundant, made of a single positive particle. Another, slightly heavier, formed by combining two types together, and a trace of slightly more complex structures, formed under specific conditions. These are the first atomic nuclei, not yet atoms in the full sense, because they are not yet accompanied by the particles that will orbit them, but the cores, the centres around which atoms will later form. There is something quietly beautiful about this stage, because it represents the first true act of construction. The universe, once a place of pure energy and fleeting particles, now begins to assemble lasting structures, simple but enduring. It is often helpful to think of this period as a kind of cosmic furnace, a place where heat and pressure, though steadily decreasing, still provide enough energy to drive transformation. But unlike a furnace that grows hotter, this one is slowly cooling, and it is precisely this cooling that allows structure to emerge. If the universe had remained too hot, these nuclei could never have formed. If it had cooled too quickly, the interactions needed to build them might never have occurred. Instead, it follows a delicate path, cooling at just the right pace, allowing these early combinations to take shape. There is also natural limit to what can form during this time. The conditions allow for the creation of only the lightest nuclei. Heavier structures require environments that are not yet present, so the universe, at this stage, becomes filled primarily with these simple building blocks, light elements, spread across vast distances, carried along by the ongoing expansion. They are not yet organized into stars or galaxies. They drift quietly through space, but they carry within them the potential for everything that will follow. There is an important detail here, one that highlights just how sensitive this process is. The balance between the two main types of particles involved in forming these nuclei must fall within a very narrow range. If there were too many of one or too few of the other, the outcome would be very different. The types of nuclei that could form, the proportions in which they appear, all of it depends on this delicate balance, and as we will soon see, even small changes in these conditions could have led to a universe where stars never form, where chemistry never becomes rich enough to support complexity. For now, though, the process unfolds just as it does. Particles combine, structures form, the first atomic nuclei emerge, simple, stable, and widespread. A quiet milestone, one that sets the stage for everything that follows. As the universe continues to expand, it becomes cooler still. The energetic interactions that once shaped these processes begin to fade, and the newly formed nuclei remain, carried forward, unchanged, into the next phase of cosmic evolution. They will wait, sometimes for hundreds of thousands of years, before the next major transformation occurs, a transformation that will allow them to become full atoms and for light, at last, to travel freely across the universe. But before that, there is something worth pausing to consider. How finely balanced this process has been, how easily it could have unfolded differently, and how the universe, in this early moment, walks a narrow path between possibility and impossibility, a path that leads, quietly, toward everything we know. As the first atomic nuclei drift quietly through the expanding universe, as these simple building blocks settle into place, there is a moment to pause, to reflect, not on what has formed, but on how easily it could have failed. Because the universe at this stage is walking a very narrow path, a path defined by balance, delicate, precise, and surprisingly fragile. If we imagine adjusting the conditions of the early universe, even slightly, the outcome could be entirely different. Not just a little different, but fundamentally altered. Let's begin with something simple: the balance between the particles that make up atomic nuclei. In the previous moment, we saw how two kinds of particles, one carrying a positive character, the other, neutral, combine to form the first stable structures. But this balance is not guaranteed. If the neutral particles had been slightly more abundant, they would have combined more quickly, forming heavier nuclei early on. The universe might have become dominated by dense, heavy matter, leaving little room for the lighter elements that are essential for long-lasting stars. On the other hand, if there had been fewer of these neutral particles, then very few combinations would have formed at all. The universe would remain filled mostly with the simplest nuclei, unable to build complexity. In both cases, the path towards stars, planets, and life becomes uncertain, or perhaps impossible. There is also the strength of the forces that hold these nuclei together. If that binding force were just a little weaker, even the simplest nuclei might not remain stable. They would form briefly and then fall apart. A universe where matter cannot hold itself together is a universe that cannot build anything lasting. But if that force was slightly stronger, something else happens. Particles would bind too easily, forming heavier structures too early, locking matter into forms that leave little flexibility for the later processes that create stars and chemical diversity. Again, the balance is narrow, not exact, but precise enough that even small changes shift the outcome dramatically. Then there is the strength of gravity, the gentle force that over time gathers matter together, shaping the large-scale structure of the universe. If gravity were stronger, matter would clump together too quickly. Structures would collapse early, possibly forming dense regions that prevent the long, stable lifetimes of stars. If gravity were weaker, matter might never gather at all. The universe would remain diffuse, too spread out to form galaxies, or anything resembling the structures we see today. And then there are the properties of light and electromagnetic interaction. The rules that determine how particles attract, repel, and form bonds. If these interactions were slightly different, atoms might not form in stable configurations. Chemistry, as we know it, would not exist. No complex molecules, no chains of reactions, no foundation for life. Each of these parameters, each of these quiet rules, sits within a narrow range, not perfectly fixed, but constrained enough that meaningful structure can emerge. This idea is sometimes described as fine-tuning, not in the sense that something deliberately adjusted the universe, but in the sense that the conditions we observe fall within a range that allows complexity to develop. It is as though the universe began with a set of dials, each controlling a different aspect of reality, and somehow those dials are set in a way that permits stars to shine, atoms to bond, and life to arise. If even one of those dials were turned slightly, the story could change. Not gradually, but completely. There is a quiet mystery here. Why these values? Why this balance? Some have suggested that perhaps these conditions are simply necessary, that they arise from deeper laws we have yet to uncover. Others propose that there may be many universes, each with different settings, and that we find ourselves in one where the conditions happen to allow observers to exist. In this view, it is not that the universe was designed for life, but that life appears only in those universes where the conditions make it possible. It is a subtle shift in perspective, from asking, why is the universe suited for us, to asking, In what kinds of universes could we ask this question at all? For now, both ideas remain open. What we can say, with quiet confidence, is that the universe we observe lies within this narrow window, a range of conditions that allows simple beginnings to grow into complexity, that allows energy to settle into matter, matter into atoms, atoms into stars, and eventually into something capable of reflecting on its own existence. There is something deeply humbling in this realization that everything we know, everything we are, depends on a balance that could have been otherwise, not by a large margin, but by the smallest of shifts. And yet, here we are, in a universe where that balance holds, where the first nuclei have formed, and where the conditions are just right for the next stage to unfold. As the expansion continues, as the temperature drops further, the universe enters a quieter phase, one where the building blocks are present, but something is still missing. Because although nuclei exist, the universe is still filled with energetic light, light that moves freely, interacting constantly, preventing the formation of stable atoms. It is a time of waiting, a time where matter exists but cannot yet fully organize, where light fills every space but cannot yet travel freely across it. And as we move forward, we will begin to explore this next transition, a moment when the universe shifts from opaque to transparent, when light, at last, is released, and the cosmos becomes visible for the first time. As the universe continues its quiet expansion, as the first atomic nuclei drift through space, something important is already present: light. Not the kind of light we see from a lamp or a star, but a vast sea of radiant energy, filling every part of the universe. It is everywhere, constant, restless, moving in all directions, and yet, despite its presence, the universe is still dark, not because light does not exist, but because it cannot travel freely. To understand this, it may help to imagine a dense morning fog. If you stand in the middle of it, even if the sun is shining above, you cannot see very far. Light is there, but it is scattered, bouncing from one droplet to another, constantly changing direction, never reaching your eyes in a straight path. The early universe is something like this, a vast glowing fog, not made of water droplets, but of particles and energy tightly mixed together. At this stage, matter is not yet arranged into stable atoms. Instead, it exists as a kind of hot, charged mixture. Particles move rapidly, interacting constantly, exchanging energy at every moment. And in this environment, light cannot travel far. Every time a beam of light begins to move, it quickly encounters a particle. It is absorbed, re-emitted, scattered again, over and over. It never moves freely across long distances. It is trapped, not in a prison, but in a constant web of interactions. A restless, glowing confinement. This means that even though the universe is filled with light, it is also opaque, not transparent, not clear, but cloudy. If you could somehow be present in this early universe, you would not see distant structures. There would be no stars, no galaxies, no horizon, only a diffuse glow surrounding you on all sides, a brightness without direction, a light without distance. It is a strange kind of darkness, not the absence of light, but the absence of clarity, everything illuminated, yet nothing visible. And within this glowing fog, matter and light are deeply connected. They move together, influence one another, forming a tightly coupled system. Light cannot escape, and matter cannot fully settle. Each depends on the other, each shaping the behavior of the other. It is a universe in suspension, a state where everything exists, but nothing is yet free. And yet, even within this fog, there are subtle differences, small variations in density, faint imprints from earlier times, still present. Light carries these variations, not as images, but as slight differences in intensity, tiny fluctuations that reflect the underlying structure of the universe. It is like a memory encoded in brightness, a record of the early fluctuations carried forward, even in this opaque state. But there is something else happening as well, something quieter and easier to overlook. Not all particles are equally constrained. Some move through this dense environment with very little interaction. They pass almost unnoticed, slipping through the fog without scattering. These are among the most elusive particles in the universe. They interact so weakly, so rarely, that they can travel vast distances without being stopped. In this early phase, they begin to move freely long before light does, while light remains trapped, bouncing endlessly. These particles escape. They carry with them information, a faint imprint of the universe at an even earlier time, a kind of silent signal moving outward, largely undisturbed. We cannot easily detect them today. They're incredibly difficult to observe, but their existence reminds us that even in the earliest moments, not everything was confined. Some traces of the past slipped quietly through. Returning to the broader picture, the universe remains in this glowing, opaque state for a long time, not moments, not hours, but hundreds of thousands of years. During this time, expansion continues. The universe grows larger, energy spreads out, temperature gradually decreases, and slowly, almost imperceptibly, the conditions begin to change. The fog does not disappear all at once. It thins, little by little. The interactions between light and matter become less intense. Particles move more slowly. Collisions become less frequent. And as this happens, something remarkable approaches. A transition. Not a dramatic explosion, not a sudden event, but a quiet release. A moment when light, at last, is no longer trapped. When it can begin to travel, not just a short distance, but across vast stretches of space. It is a gentle turning point, the universe shifting from opaque to transparent, from confinement to freedom, from a glowing fog to a space where light can carry information across time. For now, we remain just before that moment, in a universe still filled with diffuse brightness, still wrapped in its own light, a place where everything is illuminated, but nothing is yet visible. And as we continue, we will step into that transition, into the moment when the fog clears, when the first light is released, and the universe, for the first time, becomes something that can be seen. As the universe continues to expand, as the glow in fog slowly thins, we arrive at a moment that is both quiet and profound. A moment when something that has always been present finally becomes free. For a long time, light has existed everywhere, filling space, moving, interacting, but never travelling far. Always scattered, always redirected, like a voice echoing endlessly in a crowded room, never reaching a distant listener. But now, the conditions begin to change. The universe has been expanding for hundreds of thousands of years, and with that expansion comes cooling, gradual, steady, gentle. The temperature drops just enough for something new to happen. Particles that once moved too quickly to bind together begin to slow, not abruptly, but just enough. And when they meet, they are no longer torn apart immediately by the surrounding energy. They begin to stay together. For the first time, stable atoms begin to form, Not complex atoms, not yet, but the simplest ones, a small central nucleus, now joined by a particle that settles into a kind of orbit around it, a structure that can persist, a structure that no longer breaks apart at every interaction. It is a subtle transformation, but a crucial one, because these newly formed atoms behave differently. Before this moment, the universe was filled with free charged particles. These particles interacted strongly with light, constantly scattering it, preventing it from travelling freely. But now, as particles combine into neutral atoms, that interaction changes. Light no longer encounters the same level of resistance. It can move without being constantly scattered. And so, gradually, the universe becomes transparent, not in an instant, not with a flash, but like a fog slowly lifting, visibility increasing, distance opening, clarity emerging. And then, something remarkable happens. Light, which has been trapped for so long, is released. Not newly created light, but light that has been there all along, now finally able to travel freely across the expanding universe. This is sometimes described as the first light, not because it is the first time light exists, but because it is the first time light can move across great distances, carrying information, forming a visible history. If we could somehow witness this moment, we would not see stars igniting or galaxies forming. Instead, we would see a soft glow spreading outward, light beginning its long journey through space, a journey that, for some of it, continues even now, because that ancient light, released in this early moment, has never stopped travelling. It has been stretched, softened, changed by the expansion of the universe, but it is still here, all around us, faint, almost imperceptible, but present. It fills the universe as a gentle background, a quiet echo of that early time, a kind of afterglow, not bright, not overwhelming, but steady and deeply informative. It carries within it the imprint of the early universe. Those tiny fluctuations we spoke of earlier, those slight variations in density, are preserved in this light, encoded as subtle differences in temperature, small variations in intensity, spread across the sky. If we could map this light carefully, patiently, we would see a pattern, not random, but structured. A snapshot of the universe at the moment it became transparent, a glimpse into its early state, and in fact, we have done exactly that. Through careful observation, scientists have detected this faint background glow, not with the naked eye, but with sensitive instruments designed to measure even the smallest variations. Its discovery was not planned. It was not the result of searching for this exact signal. Instead, it was found by accident. Two researchers, working with a large antenna, noticed a persistent background noise, a signal that did not seem to come from any known source. They checked their equipment. They accounted for every possible interference, even cleaning out small disturbances that might affect their measurements. And yet, the signal remained steady, uniform, coming from all directions. What they had found, without intending to, was this ancient light, a remnant from the early universe, a quiet confirmation that the universe had once been hot, dense, and opaque, and had transitioned into the transparent state we now observe. There is something deeply poetic in this discovery, that a signal from nearly the beginning of time could travel across billions of years and arrive quietly as a faint background waiting to be noticed, not announced, not dramatic, but persistent, and from that faint glow we have learned a great deal about the age of the universe, about its structure, about the tiny fluctuations that would later grow into galaxies. It is like receiving a message from the past, written not in words, but in patterns of light. A message that tells us not everything, but enough to begin understanding our origins. And yet, even as the universe becomes transparent, as light begins to travel freely, it does not immediately become filled with stars. There is still a long period of darkness ahead, a time when matter exists, when atoms have formed. But before the first luminous structures ignite, a quiet interval where the universe is clear, but still dim. For now, though, we remain at this turning point, where light is finally free, where the universe shifts from hidden to visible, from a glowing fog to a space where information can travel across time. And as we continue, we will begin to explore how these patterns, carried by light, begin to shape the large-scale structure of the universe, how the faint ripples of the past become the framework of everything that follows, a universe no longer concealed, but quietly revealing itself. As the universe becomes transparent, as light begins its long journey across space, something else quietly remains, a memory, not written in words, not carried in objects, but encoded in patterns, subtle, gentle, almost invisible at first glance. These patterns are not random. They are the result of something that happened long before the first light was released. Something that, in a way, resembles sound. Not sound as we hear it, not vibrations travelling through air, but waves moving through the early universe itself. To understand this, it may help to imagine a still body of water. If you disturb the surface, even slightly, ripples begin to spread outward. They carry energy, moving in expanding circles, gradually fading as they travel. Now imagine something similar, but instead of water, the medium is the early universe, a dense, hot mixture where matter and light were tightly connected. In that environment, small variations in density, those tiny fluctuations we've followed since the beginning, do not simply sit still. They move, they oscillate, they behave like waves. In some regions, matter becomes slightly compressed, in others, slightly expanded. These changes do not remain fixed. They shift back and forth, gently, rhythmically, a kind of cosmic vibration. It is not something that could be heard, even if we had been there. But in structure, it is similar to sound. Waves of compression and expansion, moving through a medium. In the early universe, these waves travel outward from regions of higher density, pushing matter away, and then allowing it to fall back again under the influence of gravity. A delicate balance between outward pressure and inward pull. This creates a pattern, a rhythm, a gentle oscillation, repeating over time, and then something important happens. As the universe continues to cool and atoms begin to form, the medium through which these waves travel begins to change. Matter and light decouple. They no longer move together as they once did, and when that happens, the waves stop, not gradually, but effectively frozen in place, like ripples on a pond, suddenly captured in stillness. The motion ceases, but the pattern remains, a snapshot of those early oscillations. These frozen patterns become embedded in the distribution of matter. They leave behind a subtle imprint, a preferred scale, a gentle spacing in how matter is arranged across the universe. It is not obvious at first, not something you would notice by simply looking at a small region of space, but on very large scales, it becomes clear. Galaxies are not distributed entirely at random. They show faint traces of these ancient patterns, a slight tendency to be separated by certain distances, reflecting those early waves. It is as though the universe carries within it the memory of a sound that was never heard, a quiet echo from a time before light could travel freely. And remarkably, we can still detect this pattern today, not directly as waves, but as statistical features in the large-scale structure of the universe. By mapping the positions of galaxies and studying how they are distributed, we can see the imprint of those early oscillations, a kind of cosmic fingerprint. It serves as a gentle measuring tool, because the scale of these patterns, the distance between these subtle ripples, is set by the conditions of the early universe. It provides a reference, a way to understand how the universe has expanded over time, not through equations or symbols, but through patterns, through relationships, through the quiet structure left behind by ancient motion. There is something deeply calming in this idea, that the universe, in its earliest moments, carried within it a kind of rhythm, a soft, almost musical quality, not in sound, but in structure, a set of oscillations, rising and falling, shaping the distribution of matter, and that even now, billions of years later, that rhythm has not been lost. It has been preserved, stretched across space, woven into the fabric of the cosmos. If we could somehow step back, far enough to see the universe as a whole, we might not hear a sound, but we would see its pattern, a vast intricate arrangement guided by those early waves. A structure that reflects both the initial fluctuations and the way they evolved under the influence of gravity and expansion. And this structure continues to grow. Those early imprints, though subtle, guide the formation of galaxies. Regions that were slightly denser attract more matter. Filaments begin to form, connecting clusters of galaxies across immense distances. Voids expand, leaving vast regions of emptiness between them. The universe begins to take on a kind of architecture, not imposed, not designed, but emerging naturally from the interplay of simple processes, from fluctuations, from waves, from gravity, and all of it connected to those early oscillations, those silent cosmic waves that once moved through a hot, dense universe and now live on as patterns in the distribution of galaxies. As we continue, we will begin to explore another invisible influence, one that does not emit light, does not interact strongly with what we see, but plays a central role in shaping this structure, an unseen presence that guides the formation of galaxies and forms the underlying framework of the cosmic web. For now, we can rest in this quiet idea that the universe, before it formed stars, before it formed galaxies, carried within it a rhythm, a gentle oscillation that shaped everything that followed. As the faint patterns left by those early waves begin to guide the distribution of matter, as the universe slowly takes on a kind of large-scale structure, something else is quietly at work, something we cannot see, something that does not glow, does not reflect light, does not interact in the ways we're used to, and yet it shapes everything. If we look out into the universe today, mapping the positions of galaxies across vast distances, we begin to notice something unusual. Galaxies are not scattered randomly. They form patterns, clusters, connected by long, thread-like filaments, stretching across immense regions of space, and between them, enormous empty areas where very little matter resides. It is as if the universe is woven into a kind of cosmic web, a delicate structure both intricate and immense. But when we try to understand how this structure formed, something doesn't quite add up. The visible matter, the stars, the gas, the galaxies we can observe, is not enough to explain it. There simply isn't enough of it. Not enough gravitational pull, not enough influence to gather matter into these vast structures within the time available. It is as though something else is present, something adding to the gravitational effect, quietly guiding the formation of this cosmic architecture, something invisible. To make sense of this, it may help to imagine walking through a room in complete darkness. You cannot see the walls, the furniture, or the layout, but as you move, you begin to feel your way around. A gentle resistance here, an open space there, a surface beneath your hand. Even without sight, you begin to understand the structure of the room. In a similar way, astronomers have mapped the universe not only by what they can see, but by how things move. Galaxies orbit each other. Light bends as it passes through space. Clusters hold together in ways that suggest more mass than we can observe. These are clues, indirect but consistent. They point to the presence of something unseen, a form of matter that does not emit light but still exerts gravity. This is what we call dark matter, not because it is mysterious in a dramatic sense, but simply because it does not interact with light. It does not glow. It does not absorb. It does not scatter. It remains hidden. And yet, its influence is everywhere. In the early universe, long before stars formed, this invisible matter began to shape the distribution of everything else, while ordinary matter, what we are, made of, was still interacting strongly with light, still part of that glowing fog. Dark matter behaved differently. It did not interact with light in the same way. It moved freely, influenced primarily by gravity, and because of this, it began to gather earlier, forming subtle regions of higher density, long before visible matter could do the same. These early concentrations acted like a kind of framework, a hidden structure, guiding where matter would eventually collect. When the universe became transparent, when light was finally able to travel freely, ordinary matter began to respond to these existing patterns. It flowed into the gravitational wells created by dark matter, falling inward, gathering, building upon the invisible structure that was already there. It is as though dark matter laid out the scaffolding, and visible matter filled it in. Over time, this process leads to the formation of galaxies, clusters of stars, bound together, arranged along the filaments of this cosmic web. And between these filaments, vast empty regions remain, voids where little matter has gathered. The result is a universe that is not uniform, but structured, a network shaped by both the visible and the invisible. There is something quietly profound in this, that most of the matter shaping the universe cannot be seen, that the luminous objects we observe, the stars, the galaxies, are only part of the story, a visible layer resting upon a deeper, unseen foundation. And yet, despite its importance, dark matter remains one of the great mysteries of modern science. We know it is there, through its effects. We can map its influence, measure its gravitational pull, observe how it shapes the motion of galaxies. But we do not yet know exactly what it is made of. It does not behave like the particles we're familiar with. It does not interact through the same forces, except for gravity. It passes through ordinary matter, almost without notice. It is present, but elusive. Some theories suggest it may be made of new kinds of particles, ones that rarely interact. Others propose more subtle explanations, modifications to our understanding of gravity itself. But for now, The question remains open, and perhaps that is fitting, because the universe, even as it reveals its structure, continues to hold back certain answers, offering clues but not complete explanations. For now, what matters is this: the universe has gained shape, from tiny fluctuations to waves to invisible structures. A framework has emerged, a vast interconnected web spanning billions of light years, and within this web, matter continues to gather. Gas clouds begin to form, drawn together by gravity, cooling, condensing, preparing for the next transformation, because soon, within these dense regions, something new will ignite. Light, not trapped, not scattered, but produced. Stars, the first true sources of illumination in the universe, and with them, the next chapter begins. For now, we remain in this moment of structure, a universe shaped not only by what we can see, but by what we cannot. A quiet reminder that reality often extends beyond our senses, and that even in darkness, there is form. As the invisible framework of the universe takes shape, as matter gathers along vast filaments and settles into dense regions, a new transformation begins. Not in the quiet, diffuse spaces between galaxies, but within the densest pockets of gas, where gravity has drawn matter together and held it long enough for something remarkable to happen. These regions, though still dark, are no longer empty. They're filled with clouds of simple atoms, mostly the lightest kind, drifting slowly, cooling, and gradually collapsing inward. At first, the motion is gentle. Particles move, collide, lose a little energy, and settle closer together. Over time, the density increases. The cloud becomes thicker, more compact, and as it contracts, something important begins to change. The center grows warmer, not because heat is being added from outside, but because the motion of particles becomes more intense as they are drawn inward. It is like gently compressing a cushion. As the space decreases, the material inside becomes more active, more energetic. Except here, the scale is enormous, and the process unfolds over millions of years. Slowly, steadily, the temperature at the center rises, higher and higher, until it reaches a point where something new becomes possible. The particles at the center, moving with increasing energy, begin to interact in a different way. They no longer simply collide and scatter, they begin to combine, not loosely, but in a deeper, more transformative process. A process that releases energy, a process that turns the core of this collapsing cloud into a source of light. This is the birth of a star. The first stars in the universe are not like the ones we see today. They form from very simple ingredients, almost entirely composed of the lightest elements. They are massive, often much larger than our sun, and they live fast, burning brightly, intensely, for relatively short periods of time, and yet, during their brief lives, they perform a crucial role. Inside their cores, under immense pressure and temperature, simple nuclei are combined into heavier ones, step by step, building more complex elements, from the simplest beginnings to structures that were not present in the early universe. It is a quiet kind of creation, not sudden, not explosive, but steady, a gradual transformation taking place deep within the heart of stars. And when these early stars reach the end of their lives, something dramatic happens. Their cores can no longer support the balance between gravity pulling inward and energy pushing outward. The structure collapses and then rebounds, releasing an enormous burst of energy. The star explodes, not gently, but powerfully, sending its material outward across the surrounding space. These explosions scatter the elements formed within the star, distributing them into the universe, enriching the surrounding gas, adding new complexity to the cosmic environment, where once there were only simple building blocks. Now there are heavier elements, materials capable of forming more intricate structures, and with each generation of stars, this process continues. Stars form, leave, and eventually release their contents. Gradually, the universe becomes richer, more varied, more capable of supporting complexity. Over time, new stars begin to form from this enriched material, not just simple clouds, but clouds containing a mixture of elements. And around some of these stars, and something new begins to take shape. Disks of gas and dust, rotating, slowly, flattening, and gradually forming small solid bodies. These bodies collide, combine, and grow. Some become planets, worlds with surfaces, with structure, with the potential for further change. On some of these worlds, conditions allow for the formation of molecules, not just simple combinations, but increasingly complex ones. Chains of atoms, linking together, forming patterns, interacting in new ways. Some of these molecules form even in the vast spaces between stars, within cold clouds, shielded from intense radiation. Chemical reactions occur slowly, patiently, building complexity over time. Fragments of these molecules can become part of larger structures, carried by dust, incorporated into forming planets, delivered by impacts from small celestial bodies. Over long stretches of time, these processes can lead to something extraordinary. Systems where chemistry becomes dynamic, where molecules interact, combine, replicate, and evolve, where simple patterns give rise to more complex ones. Eventually, under the right conditions, this can lead to life, not immediately, not easily, but as a continuation of the same processes that began in the earliest moments of the universe, from fluctuations to particles to atoms to stars to planets, and finally to living systems capable of observing, thinking, and wondering. There is something deeply humbling in this progression, that everything we are, every element in your body, was once formed inside a star. The calcium in your bones, the oxygen you breathe, the iron that flows through your blood, all of it, forged in stellar cores and scattered across space. Long before the Earth existed, we are not separate from the universe. We are part of its history, a continuation of its evolution. And yet, even as this story unfolds, even as complexity emerges, the universe remains vast and largely empty, filled with countless stars, countless galaxies, each following its own path, shaped by the same underlying rules. And within that vastness, only certain regions give rise to the conditions needed for life. A reminder that while the universe allows for complexity, it does not guarantee it. For now, we can rest in this moment, a universe that has moved from simplicity to structure, to light, to life. A quiet unfolding, spanning billions of years, leading from the smallest fluctuations to the richness of existence. And as we continue, we will turn our attention to something that still remains unresolved. Because even with all that we have learned, the universe holds on to its deepest mysteries, questions that remain open, waiting, quietly, at the edge of our understanding. As we come to the quiet edge of this long journey, from the earliest flickers of existence to stars, planets, and life, it might feel as though we have arrived at an answer. Complete story, a beginning, an unfolding, and a result. And in many ways, we have. We understand more about the universe today than at any point in history. We can trace its expansion, map its structure, and follow the path from simple particles to complex systems. And yet, something remains, a gentle, persistent sense that the story is not finished. Because even as we uncover layer after layer of understanding, the universe continues to hold on to its deepest mysteries. One of these mysteries lies in the way the universe expands. For a long time, it was assumed that this expansion, which began in the earliest moment, would gradually slow down. Gravity, pulling everything inward, was expected to act as a kind of brake, not stopping the expansion entirely, but easing it, reducing its pace over time. But when we looked more closely, when we observed distant galaxies and how their light reaches us, we found something unexpected. The expansion is not slowing down, it is accelerating. Galaxies are not just drifting apart, they are moving away from each other faster and faster as time goes on. It is as if the universe, instead of coasting, has gently pressed down on an unseen accelerator. Something is driving this motion, something that acts on the larger scales, influencing the expansion of space itself. We do not see it directly, we do not detect it in the way we detect matter or light, and yet its effect is clear. It shapes the future of the universe. This unknown influence is often referred to as dark energy, not because we fully understand it, but because it describes something that cannot yet be explained in familiar terms. It appears to make up most of the energy content of the universe, and yet its nature remains elusive. Is it a property of space itself? A kind of energy that exists even in empty regions? Or is it something more dynamic, changing over time, evolving as the universe expands? For now, we do not know, and alongside this mystery, there are others. We have spoken about dark matter, the unseen presence that shapes galaxies, but we still do not know what it is made of. We have traced the origin of matter, but we do not fully understand why there is more of it than its mirror counterpart. We have described the earliest moments, but we cannot yet fully explain what happened at the very beginning, when our theories begin to blur. There are even questions about the structure of the universe on the larger scales. Observations of distant galaxies, of early structures, sometimes suggest that things formed earlier or differently than our current models predict. Not enough to overturn our understanding, but enough to remind us that our picture is still incomplete. There are also ideas that stretch beyond what we can currently test, possibilities that suggest the universe we observe is only part of a larger whole, that there may be other regions, other universes, governed by slightly different rules, or that the constants we observe, the strengths of forces, the properties of particles, may be just one set among many. These ideas remain speculative, carefully considered, mathematically explored, but not yet confirmed, and so they sit at the edge of our understanding, inviting curiosity, but also patience. There is something important in this, a quiet balance between knowledge and uncertainty. Because science does not aim to remove mystery entirely, it aims to understand, to explain, to reduce the unknown, but never to eliminate it. Each answer often reveals new questions, each discovery opens new directions, and the universe, in its vastness, ensures that there will always be more to explore. Perhaps that is part of what makes it so calming to reflect on, that even as we learn, even as we map the cosmos, We are still participants in an unfolding story, not observers standing outside it, but part of it, formed from its processes, shaped by its history, and capable of reflecting on its nature. There is also a quieter perspective, one that does not focus on what we do not know, but on what has already emerged. From an early state of energy, structure formed. From structure, stars ignited. From stars, elements were created. From those elements, planets formed. And on at least one of those planets, life appeared, not as an inevitable outcome, but as a possibility realized. And from that life came awareness, the ability to look outward, to ask questions, to trace the story backward, all the way to the beginning. It is a remarkable arc, not because it is complete, but because it exists at all, a universe that can give rise to something that wonders about its own origin. And perhaps that is enough for now, not a final answer, but a quiet understanding that the universe is both knowable and mysterious, structured and open, simple in its rules, yet capable of producing extraordinary complexity. As we reach the end of this journey, you might notice that the questions we began with have not entirely disappeared. They have changed, softened, deepened, but they remain, and maybe that is how it should be, because the universe is not just a problem to be solved, it is something to be experienced, something to be explored, slowly, gently, with curiosity and wonder. And so we come to rest here, at the edge of what we know and the beginning of what we do not, and wherever you are, whatever time it is, you're part of this story, a small, quiet expression of a universe that began long ago and is still unfolding. And so we've reached the end of tonight's exploration. Whether your eyes are still open or you're already floating somewhere between waking and dreaming, thank you for being part of this little journey. If you'd like to join me again for more gentle wanderings, you're always welcome to subscribe or share this with someone who could use a peaceful pause. Time has a way of slipping through our fingers, but here, in this quiet moment, it's just you and the soft hush of rest. Sleep peacefully, wherever and whenever you may be.